Alright, time for another draft. Science. Really is science. Video presentation. And, it is kind of funny that all the naysayers are just sort of mocking the idea that it is actually science. All of this. I guess I could leave that up there, actually. So the Ian Gosling has done what was requested, partially, a tiny bit of what was requested, but anyway, it's enough to draw the conclusion. So, I use my little pointer. This is the two mass at half the distance. This is the two mass at twice the distance. So, clearly not the same. Now, it should be the same energy, it's the same spring, it's pushing the same lever, and clearly what is indicated here is that the weight of the lever is playing a significant role. The lever consumes less energy the further out you put the object. Now that would say to you, well, then the lighter object should go even faster. Catch. Okay. So anyway, but yeah, so clearly the lever isn't doing what an ideal lever would do. That is one that had zero mass and 100% rigidity. Because technically the spring is basically just pushing the weight, and that's all that matters. Now, what I didn't consider is the fact that the weight of the lever does actually matter. Even though it's the same weight of the lever in both experiments, the fact is, as a percentage of the total weight, that weight is significant. So, I was thinking the lever was 1/10 the weight, like it was light aluminum or something. It clearly weighs like half as much as the weights themselves. It might even weigh the same amount as the half mass. So the lever is consuming an enormous amount of the energy. And that's the root of the problem. So I will explain and such. But you can see, rather dramatic difference. You could almost argue that this is almost twice as high in gravity. I did cheat the pictures a little in the sense that this is a little lower, actually. This one's a little lower than it actually went. So it actually did meet the line, and this one's about at the line. So you can just say that it went a full mark higher, which is significant in gravity. It doesn't equal twice, because you have to go 4 times and all that kind of stuff, but it's a significant amount of extra energy, velocity. Significantly more. Not a little bit more, significant, 33-40% more energy. And you really shouldn't have that kind of variability. Certainly you wouldn't with ideal. So we're way far away from ideal. Alright, so we probably don't need that anymore. And we won't play. He's made, so this is the video where I got those images from. So it's a simple video. He just takes the two mass and launches it from the two locations, and as you see, there's a big difference in the amount of velocity it gets depending on where you put it on the lever. Theoretically, it shouldn't be a great deal of difference. Alright, so on to the science. Alright, and look, this is all stuff I hadn't considered. It's, you have to really spend some time fiddling with this crap before you can rock all of the variables that are affecting the outcome. So the idea would be, let's say the lever weighs 10. It weighs, significant amount. Half the weight. It's the same weight as the two mass, let's just say. If that was the situation. And you can understand that when I put the 5 mass on it, the total is 15. And the 10 plus the 10 is 20. So if I have a 20 at half, at this distance from the fulcrum, and I want to go and make it a 10 essentially, okay, I cut it in half. This won't work, okay. So because this will equal 10, I'm looking for the number 10. And what do I have when I put the half mass here? I still have 15. So I have to actually move this further out. Just like the double mass will go further, right? So you put the two mass here, it goes this far. puts the 2 mass out here, it goes this far. The same is true for the half mass. So if I want to get more velocity, which I want as a percentage of the weight of the lever, I have to go out further. The real twice the distance has to do with the halving of this total here. You have to halve the 20. And to have the 20, you have to reduce the weight of the lever. That is the work the lever's doing. So that if they're doing the same work, if the lever's moving the same way, okay, in the circumstance where I put the 2 mass here and I put a 1 mass here, the lever theoretically would move identically. But the fact is the weight of the lever has to be included in the calculation of where this halfway point is. The halfway point has to be the half of the weight point. So where do I half the weight? Well, I'm only half the weight where I'm telling the lever's doing, obviously, the lever does less work, does less movement. Okay, here. Total movement of the lever is less out here for the same velocity. So if I shoot something at just 5 velocity, and I shoot from 5 velocity, you can understand that the work the lever's doing here to make 5 has to be more work. It has to move faster than if it's moving this far, because this is a bigger arc. So technically the lever moves the same to create this as it does to create this. Technically. And so if I want to get this increase in velocity, I actually have to do half of 20 to get the 10. So I have to make the lever move less. So moving the same amount, moving the same as this distance won't work. This won't be twice. You have to go out here to get twice. You have to go where you're where you reduce the amount that this is consuming, okay, and giving it to this. That's the real half. You have to reduce how much the lever's consuming as a percentage of the total mass. So another way of just thinking of it is that you have to include the mass of the lever in understanding how much this actually weighs. So I could put a 10 here, but it's a 10 plus the weight of the lever, understand? And this is a 5 plus the weight of the lever. So 15 obviously isn't half of 20. You can sort of get it, right? 15 isn't half of 20. So I have to go out further to get to 10, where the total used, the energy used, the simple point is that this one goes further, okay, with the 2 mass here. The 2 mass did this. This is what it did. It's going further because the lever's consuming less of the energy. The further out I go, the less energy the lever's taking as a percentage of the total energy. It's doing less movement, and this is doing more movement. So instead of moving the lever, here you're moving the lever a lot, and you're moving the mass less, and here you're moving the mass more, okay, and moving the lever less. I could draw that better, but you should be able to get the idea, right? So the lever moves less to create speed, the same speed. So if I want to create the same speed, this one has to, the lever itself has to move more. If I put it out here, the lever itself has to move less to move the same distance in the same amount of time. So the lever's consuming less of the energy the further out I put it. So you can simply, like I said, the math is kind of obvious that 15 isn't half of 20. So I have to put this at a place where the lever's consuming less. I have to reduce this 10. If I have the same 10, that is, the lever has the same movement, that is, it's consuming the same amount of energy, then I'm stuck with an inequity. So I have to move this far enough to make the lever only consume 5. I have to make the lever seem like it only weighs 5. So then my 5 mass will equal 10. So I have to put the lighter object out here to get the full effect. So yes, unfortunately catapults have a liability. The catapult, the lever part, can't weigh okay, anywhere near as much. The more the catapult weighs, the more it's an influence. The less it weighs, the less relevant it is. And that's a real problem. And obviously, the less it weighs, then we got the bending problem, we got all these other problems. But clearly, the less it weighs, it's important. And I didn't think it matters, but you can sort of intuitively understand how it must matter. Okay, because the fact is, it does change its speed depending on where I put the mass. And that means that I'm moving more or less lever, and that explains the dilemma. So anyway, so it's a little, it's not that abstract. People really should be able to understand that you really are moving. You really have to think of the object and the lever as one object. That's what the spring is seeing. The spring is seeing one object. It's seeing the mass of the lever and the mass of the object. It's not just seeing the mass of the object. That's the downside of the horizontal lever, because you don't have a gravity thing where one side does the opposite of what the other side does, and so they don't steal any energy from each other. You know, you can make a teeter-totter out of a 10-ton piece of steel, and it'll work just as well, because it, you know, frankly, it, whatever you're using going this way, you're getting back going this way. I mean, whatever you're using going up, you're gaining by going down on the other side. So, yeah, that's probably enough said. You do really have to think of this as one unit. And half of this is not this. You have to put it out here. So the lever takes less, and you can give the extra to the object, the 5, to make your 10. Alright, so I think that explains it. So my bad for not realizing that, you know, I said you don't have to worry about the weight of the lever using a catapult, but there's a limit to that statement. And, you know, obviously the limit is if the lever's half the weight or more, then it's going to be a real problem finding the distance that's twice the distance. Just ain't going to be that simple. Alright, so on to the next video, where he's going to spend 3 minutes explaining inertia calmly this time. There's no, he keeps just ignoring. Okay, again, I'm not being insincere, but I mean, I really don't want to play quotes of, you know, or whatever his name is, the guy with 3 names. You know, all the people scientists who have quoted, you know, even Lewin, stating that inertia is just mass. So there's a ton of videos out there called inertia something or other, and they'll basically explain that, yes, inertia just means mass. So the heavier something is, the more inertia it has. So he's making this argument that somehow light things have more inertia. Alright, and it's like insanely unintuitive, let's just say. It doesn't make any sense. Alright, so again, what you have to explain, I mean, I've done these videos over and over again, is that what you're saying really doesn't show in reality. Okay, so if I have a gun, alright, where's the inertia issue? This goes with, according to your theory, 2 joules of kinetic energy. Right? That's it. And this little bullet, the little light thing, the thing that weighs 1,000 times less inertia, less mass, okay, that thing has 2,000 joules of kinetic energy. Now, I'm arguing that they have the same momentum, so the MV is the same for the 2 objects, so we don't have a problem. But clearly it seems that light things want to absorb energy even more than heavy things. That would be the conclusion. If this is the only experiment you have, you would certainly conclude that, oh, it looks like inertia really affects heavy things more. Heavy things can't absorb any energy at all, and light things really absorb energy so well. I mean, that's the obvious conclusion. All this is a little explosion in here, right? I mean, you're saying it should be 50-50. Whoa, no, the heavy thing doesn't do shit. The light thing does all kinds of crazy crap. So that was it. Okay, obviously inertia would mean, oh, the light thing should go fucking 500 miles an hour, like the bullet, you know, when the action happens. And the heavy thing, oh, shouldn't even get it off the ground. It's so heavy, it can't move. Then we have the physicist Michael experiment, right? Where we have the same exact spring compression. We put a heavy thing, you know, let's use the real example, 3 mass. We put a 3 mass there, right? And then we have the 1 mass, okay, here. And what happens when we, boom, let the explosion happens? Well, in this weird case, all right, we get a 100 here and a 100 here. And in this case, we get a 300 here and a 300 here. Okay, so we get a total of 200, you know, action, total joules. You know, you have 2002 here, right? 2002 total bits of energy in the universe. Well, you have 200 here, and you have 600 here. You know, 200 to 600. Well, his answer was more like, maybe it was a 2. Yeah, I think this was a 2, frankly. All right, so it's a 2 mass. And he doubles the amount of energy. So we have, so I should change these numbers too, just to be accurate. Okay, 2. So we have 200 joules here, and 200 joules here, and 100 joules here, and 100 joules here. So light things, wow, I lost half the energy of the spring. Half the energy of the spring disappeared because I put a light thing in front of it. And, you know, when I put heavy things in front of it, I gain twice as much energy. So if this was the only experiment you had in the universe, well, gee, the obvious conclusion is heavy things absorb energy really well and light things absorb energy really badly. Light things have a lot of inertia. You know, even though they don't have any mass, they have lots of inertia. Less mass, more inertia. That doesn't make any sense. So I'm just saying, obviously this subject of inertia is nonsense, and there's real reasons for these outcomes, and those should be dissected rationally instead of just putting some silly word inertia on here and saying inertia explains these 2 experiments. You can't explain why heavy things are absorbing more energy in this experiment and light things are absorbing more energy in that experiment. You can't do it. And so we're back to the lever. He's saying somehow the 1 mass here and the 2 mass here, that somehow the magical inertia, okay, says this can't be moved twice the velocity. It's against the rules. Now the gun says it can. The gun says, shit, it should move like 10 times as fast. I mean, it's the same explosion, same spring over here, same explosion. I mean, it should just zoom that little thing right off of there. No problem at all. There shouldn't be any inertia if guns work. So if guns work, then there have to be some other explanation for why you're not getting your extra energy here. You can't claim inertia. Inertia isn't an answer. Okay. So he's obviously not going to deal with the real subject, which is comparing light things getting hit by energy to heavy things getting hit by energy, and explaining why light things can't absorb the energy except in a gun. Somehow everywhere else, the light thing completely fails to move. But it loves to move when it's shot from a gun. No, he's not going to be able to explain that. Not going to happen. Prediction. He's not going to touch on the subject. He's doing the same stupid piece of shit experiment, proving nothing. Okay, yeah, absolutely nothing. Obviously, you move something fast, it takes more force to move it fast. Nobody's surprised by that. I just can't believe what an obnoxious idiot he is. To think this is going to explain the paradoxical duality. No, you're not going to explain it by lifting a weight. Oh, shit. I don't even know why he thinks this is an argument in any sense. How it explains anything. He's not comparing two things. He's not showing me a light thing and a heavy thing and then showing me how the light thing can't be moved because it has more inertia. Where's he showing that? Where's he showing me throwing a baseball, let's say, and it weighs 10 pounds and I have one that weighs 5 pounds? Where is he showing me that, oh shit, I can't push that 5-pounder? It just won't go twice as fast. Where's he showing me that? Nowhere. Wasting time.
This scale is shown about 1 kilogram.
So he's doing the same exact thing again.
As I move the weight up and down, accelerating.
Yeah, you're not accelerating it. You're decelerating it, and you're doing it against gravity. You're moving it slower than the force of gravity.
The weight slowly. The scale doesn't move. If I jerk it up, it's gone up to 3.5.
Yeah, you have to add more force if you, in fact, are pushing something faster up against the gravity. That's the price you pay. That's what gravity is basically saying, is it's going to get heavier the faster you try to move it.
It registers.
It's weight. That's what weight is. I mean, I've made all these videos. It's just amazing, pointing out how I move something 1 mile an hour against the scale, and it reads its mass. Okay, its atomic mass. 1 mile an hour. I take an elephant. 1 mile an hour. It weighs 1,000 pounds. I take a mouse, and it weighs whatever, 10 ounces. I mean, he just ignores all of the arguments. I mean, again, what's the point? You're not debating me. You're not engaging in a debate. You're not doing anything. This is useless nonsense because it doesn't deal with the subject. The subject is, why do light things have a hard time doing exactly what you just did? Show me how the light thing does something different. Something half the mass doesn't obey exactly the same rules, except it will change its weight by 1/2 because it's half the mass. You're doing a gravity experiment. It's not a complex thing you're doing. You're just saying how much work does it take to fight gravity. Oh.
Otherwise, I pull the weight down, it registers the highest reading. So although the weight is only 1 kilogram, I can make the scale register more.
Duh. And I've been doing balances and levers all this time, talking about the one mass weighing twice as much when it's twice as far out. What's news? There's no news here. Oh, pathetic.
By accelerating upwards on the scale. Now, not a single person on this planet would disagree with that at all, unless there was something wrong cognitively. Okay, Gary?
Yeah, what did you prove? How did you show that lighter things are harder to move? How did you show that the 5 mass further out, twice the distance on the lever, somehow weighs more than 10? Right? That's all you're doing. You're just saying, well, it weighs the same as the other mass at this location. I put a 10 mass on the other side, 1 unit of distance, and the 5 mass now weighs the same as that 10. How does that thing now move as if it weighed 15? Why is it weighing more? Okay, it's harder to move. Oh, fuck. What an asshole.
Nothing wrong so far. The weight stayed the same, the mass hasn't changed, but the force required to accelerate it is greatly increasing.
It's not increasing, it's always the same. If you move something faster, look, Newton said it. You want something to go twice as fast, you apply twice the force. You want something to go 3 times as fast, you apply 3 times the force. I mean, that's a fact. All right, and you're not refuting it with this stupid fucking nothing experiment. Where are you refuting the fact that the mass always has the same mass, and all you're saying is I'm going to add a velocity. I'm going to increase the velocity. So instead of going 1 mile an hour, I'm going to go 2 miles an hour. Well, if I go 2 miles an hour into the scale, guess what? I'll weigh twice as much.
The weight that the scale sees is much greater because of the acceleration.
So how many fucking useless times are you going to say the same useless shit over and over again? And what's the nature of the acceleration? What's so special about the acceleration? You're just changing the velocity. Is it going 1v? Is it going 2v? Is it going 3v? Well, if it's going 3v, then it's 3 times the work as going 1v. Where are you refuting that fact?
This is something in common experience. Nobody would disagree with me.
Well, it seems you do disagree. You think it takes 16 times the fuel to go 4 times as fast. Okay, you think that's a fact. Have you ever mentioned it? Have you ever said it? Will you please comment somewhere on that as a subject? Do you really think it takes 25 times the gasoline to go 5 times as fast? So I go from 10 miles an hour to 50 miles an hour, and I'm now using 25 times more fuel? You believe that's true, fuckhead? You're such a stinking invading crap to do this nonsense lesson for the retarded, okay, when you just keep running away from your dilemma. Do you really think denting clay with round objects is a sensible way to measure energy? Answer the question.
And the faster we accelerate it up, the more weight the scale will see.
Yeah. Twice the force to go twice as fast, 3 times the force to go 3 times as fast, 4 times the force to go 4 times as fast. Where are you showing anything other to be true? Oh, that's right, you're not. You're just talking babbly, infantile shit instead of making something called a physics argument.
Nearly 5 now. It's exactly the same things happening on the lever.
Bullshit. So again, exactly the same thing. Where did you compare a 5 to a 10? Where did you show me how the 5 mass in the 10 location, that is, it now weighs 10, where did you show me that somehow the universe knows it's a 5, and like the gun, oh wait a minute, not like the gun, yeah, it's going to somehow be crippled and it can't make the lighter thing move faster. You can't do it. Can't do the rational 2-to-1 thing.
On the end of the lever, the radius would dictate.
The radius is exactly the fucking same. Again, there's no such thing as any angular momentum. This radius is going to be exactly the same as the linear directional velocity. There's no fucking goddamn difference. It's a 2-to-1 relationship. This will go twice as fast, this radius, okay, as this radius. Okay, there's absolutely no difference. It's a 2-to-1 relationship. The radius doesn't mean a goddamn thing, you fucktard.
The velocity is doubled.
Yeah, duh. Duh. But it didn't happen in the experiment, did it, fuckhead? And you're saying there's some magical inertia that stopped it from happening.
To halfway along the lever, if the lever was moving at the same velocity. Quite right. But because the lever is now seeing a greater weight than it...
Why is it greater? Explain to me how the 10 mass here, okay, it's obviously becoming heavier and heavier. How is it any different than the 5 mass out here getting heavier and heavier? You just did the experiment where you had the 10 mass here and you put the 10 mass way out here and the 10 mass got lighter. It moved faster. What's your explanation, shit for brain?
Static weight.
So why? Why is this static weight here? Why did the 10 mass out here go faster? faster. No inertia problem.
Requires much more force to accelerate it.
Says you. Okay, with zero evidence. Zero evidence it takes more force to move a 5 mass, okay, at 10 miles an hour than it takes to move a 10 mass 5 miles an hour. You have no evidence that 10-ton trains going 5 miles an hour will completely be wiped out by 5-ton trains going 10 miles an hour. That 5-ton trains going 10 miles an hour takes more fuel to make a 5-ton train go 10 miles an hour than it takes to make a 10-ton train go 5 miles an hour. Where have you shown it takes more fuel to create those two things? You have any evidence of it at all? No. All we have is these balance things, and I just went through the process of dissecting the mistake we've all made, obviously, in not considering that the weight of the lever screws the math. And if you really want to get twice the velocity, you have to negate how much energy the lever itself is stealing.
Obviously, that half-pound mass on the end of the lever, and in the static balance situation.
And it keeps talking about static. I mean, there's no fucking such thing in gravity, you fucking fat ass. You have a big fat ass. When you're sitting in a chair, does your ass feel like it's doing something static? You're not noticing that it doesn't seem very fucking static because the whole fucking thing starts to ache and hurt and itch and do all these bullshitty things if I put you in a chair long enough. So obviously it's not static. There's no static happening here. You're getting hit by an active force every single goddamn fucking millisecond. It is pushing you into the ground, and the ground every fucking goddamn millisecond is pushing you back up. That's the truth. There's no fucking static. Moron.
Becomes a 5-pound mass, say, as it's accelerated. And it's the same thing as jerking up the weight. The weight becomes...
Jerking. Jeez, you should talk. I cannot believe this is the best he can do. So again, I've drawn this stuff so many times. I mean, I'm just pleading with you. Draw the 5-ton train. You make it into a 10-ton. You add 5 tons. It's now a 10-ton train, and it conserves the momentum. It still has all of its momentum. Explain to me how it could lose half the kinetic energy. Explain to me how, let's say, it could put a dent in something without using the momentum. Explain that.
More. The weight on the scale is more. The weight on my arm is more. The weight on the lever is more. The weight on the spring is more.
Yeah. You want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you have to apply 3 times the force. No surprise. You're saying it takes 25 times the fuel to go 5 times as fast. Okay, that's your theory. Explain that. Show that. But don't pretend this shows it. You're certainly not demonstrating it here. You're not showing me that if I do the 5-ton train in one hand and the 10-ton train in this hand, that somehow the 5-ton train just, oh boy, that really consumes energy to move it.
Therefore, it won't go at twice velocity. You won't find a single person on this planet who would disagree with it, Gary.
What disagree with what? What the fuck did you say? Well, it takes more energy to move something faster. Yeah, the whole question is how much more, fuckhead. That's what we're disagreeing about. I'm saying it takes 2 times the energy. You're saying it takes 4. I'm saying it takes, let's say, 5 times the energy, and you're saying it takes 25 times the energy. Fuckhead. God. I mean, how distant from the fucking subject could you possibly get? I mean, this is so fucking stupid. This is like translating. Oh, let's translate a language. Well, do you know that the paper has to be a different color than the ink, or you won't be able to read the words? That's translating? No, that's fucking goddamn nursery school. Where did you show that it takes 5 times the energy? Where did you do that? I mean 25 times the energy to go 5 times as fast. Where did you do that in this bullshit? Where did you show that it takes more energy to move a half-mass object twice as fast? Where did you show that in this fucking useless demonstration? Now he's in the garage. I wonder if he has a car in it usually. Boy, that's a nice open space. I wish I had that. Yeah. Oh, God. Space. I need space. Alright. God. Inertia explained calmly. So where did he do anything here with it? And he's got this little fucking jackass crying con thing. What the fuck is that shit? Oh, puke. You really are little children. Little toddlers. I mean, I really should just put pink balloons in the video, right? Because that would entertain you. Oh, puke. God, I hate this planet. Alright, so that's enough of a video. Alright, so I think I have provided the explanation. Now, the solution to the problem, that's the tricky part. Because it is a sort of a calculated solution. So the fact is that you can imagine that you can't put the 2 mass infinitely far back. But you could figure that if you move the 2 mass in on the lever 2 inches, and you move the 1 mass that you had twice the distance, and you move that another extra 2 inches in the other direction, that you will get your 4-to-1 relationship. You'll get the 2-to-1 relationship in terms of velocity, and it's factually correct because what you're really doing is compensating for how much the lever is diluting the experiment. Unfortunately, the weight of the lever is completely diluting the masses of the object, and that's the problem. So I thought it was benign, but it's not. So we're back to maybe we have to do the yeah, we're back to damn it, yeah, I mean how to get a light enough lever for the masses we're using. You either got to use heavier, it's like I say, you can't really use heavier masses, so you know, I have to think about the solution. Maybe you have to go. Maybe we just have to go to gears or something else. I mean, some other form of a lever where the weight of the lever isn't going to play a role. Shit. I mean, you don't really have to worry about bendable gears. So, you know. Yeah, but obviously they're going to have a weight, and you're going to have to move the weight of that, and it's so yeah. I'll think about it. It's got to be a solution.